Our last piece for this section is a discussion of something called the natural base. So if you were to look at the compound interest formula and begin to compound the interest more and more frequently from once a year, twice a year, 4 times a year, if you could keep on compounding as fast as possible, almost hourly, once per minute, once per second, and looked at the value of an account, notice that it begins to approach a same number. Here, the last few start at 2.71, and then the last digits change a bit, but not too much. So what this is showing us is the value of this expression as n gets very, very large. As n gets very, very large, we call the value of this expression the number e. So e is an irrational number, just like pi is an irrational number. And it's the value of this expression as n increases without bound. And you might wonder, well, why do we use the letter e to denote this? E stands for the Euler number. And Euler was the mathematician who first studied and introduced this number. So that's why it's called E, the Euler constant. And roughly it's about equal to 2.71, if you wanted a little more accuracy, 2.718, 2.7188282. But it goes on forever, just like pi is about equal to 3.14, about equal to 3.1457, and you could keep on going as you want to. Now, the reason it's called the natural base is because the E appears as a base in models of many, many, many naturally occurring phenomena that grow or decay. So let's take a look at something called the continuous growth model. So the continuous growth or decay model is a function that looks like this. A of t is equal to a e to the rt, where a is the initial amount, r is the continuous growth rate per unit of time, and t is the elapsed time, and e, notice, is not a variable. E is the Euler constant. So let's take a look at some examples. A person invests $1,000 in an account paying 5% interest compounded continuously. How much will be in the account in 1 year? So compound it continuously means we'll be using this compound continuous interest formula. A of t is equal to a e to the rt. So our initial amount is $1,000. Our rate is 5% as a decimal 0.05, and we're going to leave it in the account for 1 year. So the amount would be equal to 1,000 e to the 0.05 times 1. And if we take a look at that on our calculator, 1,000 times e to the 0.05, we would find out that the account would be worth about $1,051.27 in 1 year's time. Let's take a look at a decay model. Radon 222 decays at a continuous rate of 17.3% per day. If there is 100 milligrams of radon 222 in a petri dish, how much will there be in 3 days? So for compound decay, instead of growth, which is positive, decay is negative. And so we have an R value, which would be negative. So A of t is equal to a e to the rt. And for our rate, we're going to put in r is equal to negative 0.173. Our initial amount is 100 milligrams, and our time measured in days is t. So we would have 100 e to the negative 0.173 times 3, and if we work that out on our calculator, that comes out to be about 59.5. So 59.5 milligrams would be remaining in 3 days. Here's one for you to try. A certain radioactive substance decays at a rate of 12% per day. If a scientist starts with 50 milligrams of the substance, how much will be left after 7 days? So you're going to take this continuous decay formula, A of t is equal to A e to the RT. Here is your initial amount. Here is your decay rate. Don't forget to make it negative because it's decaying, and we're interested in the amount after 7 days. So go ahead and give that a try.